So let's see how this went for you. So to find A, that's that dimension across the bottom. So really what we're looking for there is hypotenuse of a triangle. This is A. What's this side down here? 2.50, and this side here, 1.10. So how do we find A? Perfect. A squared plus B squared equals C squared. So 2.73, I guess we'll call that. Okay. Next, I wanted to find angle B. Angle B is right there. Now, I could use A, but we just calculated A. So let's try to avoid using it if we don't have to. So how are we gonna find angle B? Perfect. Inverse tangent of 1.1 over 2.5. Now, the way you said that, 110 over 250, would that still work? Yeah. Yes. Yeah, as long as you did it to both of them, 110 over 250, it would still work because it's the ratio of the sides that matters, not the actual size. You could double them, both of them. You could triple both of them. You could take both of them times 127. As long as the ratio between them is the same. It's still a similar triangle, and all similar triangles have the same angle. That's why trig works, is because when you have a right angle, as long as one of the other angles is the same, the triangles are similar. So for D, we're looking at a triangle, looks something like this. D is that hypotenuse. What's the bottom of it? That's 250. What's this here side? That is the 0.65. So of course, to find D, A squared plus B squared equals C squared. .58 inches. F, perfect. I purposely did that opposite angle there because a lot of people would want to put the shorter one over the longer one, but it doesn't work. We've got to have the opposite over adjacent. Second, 2.5 divided by 0.65, 75.43 degrees. Now M is a little confusing until you realize, yeah, it's just part of this right triangle right here. Yeah, we already found A to be 2.73. This is 0.65, so M is A squared plus B squared equals C squared. 2.81, we'll call it. Now, a couple of comments here. We ended up having to use the 2.73 that we calculated up here in order to do more calculations. We only kept it to 2 decimal places because all of our other measurements are in 2 decimal places. And generally, as a rule, whatever your measurements are given in, that's what you round off your answers to. However, since we had to use that answer in another calculation, to reuse it, we should have kept at least 1 more decimal place. We didn't here because we didn't realize we were going to have to reuse it. But a lot of times when you do these calculations, you should, even though you know you're going to keep it to 3, you should write it down, or sorry, you're going to keep it to 2 decimal places. You should write it down to a 3rd, maybe even a 4th decimal place, just to make sure that your round off error doesn't build up. because this is what, 2.72 something. We rounded it up. Well, down here we get 2.806. Well, that 06 might have been an 04 if we hadn't rounded this one up. Does that make sense? So it might have been 2.80 instead of 2.81 when we rounded that. Okay, you guys had a test from last Thursday. Did you guys have that done or any questions on it you want to answer? Okay. Forgot stuff at home today? Ah. Okay, so what we are starting on in this next unit, it'll take us about 3 weeks, is we're looking at compound angles. We'll have a week left. Don't worry, we'll have plenty of time for other fun. Usually what I'll do if we have time left over is we'll do some basic statistics. We've had a couple of years where we've had like 2 weeks. Then I can do some basic statistics and a little bit of SPC with you guys. But it's been a long time since I've had time to do any SPC. Just because we always seem to lose class periods to weather and other crap. Slow us down. The SPC stuff is actually kind of fun. Have you guys done anything with like run charts? The math behind it, once you see the math behind it, it's really kind of cool. The whole, you guys ever work with a company that does Six Sigma training? A lot of machining companies, they do what's called Six Sigma training. That's just all your quality control SPC stuff. Anyway, compound angles. Compound angles kind of go off of that last piece that we saw up here in this problem, where we had to find M, but to find M, we had to know one of the diagonals of one of the other sides. The goal of compound angles is to line stuff up. What do I mean by lining stuff up? Well, let's start out with this block. Pretend that's a nice square even block. And we're going to go with 3.000 inches down here. Well, we are machining, so we usually go to the thousands, at least not to the 10th. So I'm going to give you those measurements of the block. This block is sitting, let's say that it's up against this edge here. So that right now this line here is parallel with this side. What we want to do, we want to take this line across the bottom of the block. And we want to rotate this block so that that line, so the block is rotated, that would be the bottom of the block now. So that line is now parallel with this side over here. Does that make sense? So if you're looking at it from the top, here's that blue border. Let me actually put it in blue. Here's that blue border. Looking at the block from the top, here's the block. Here's the corner to corner on bottom. We want to rotate it. So the block is turned so that that line, that green line right here, is now parallel with this. How far do we have to rotate it? Well, if we look at this from above here, there's an angle. I mean, this is the edge of the block, right? That's also where that line ended up when I rotated it, isn't it? Right on that edge. Well, how far did I rotate it? I went from here to there. So that angle is just this angle right here. So if I look down here, that's just that angle right there, isn't it? Is there another spot on this that has an exact same angle? Right here, isn't it? Either one of those two angles should be the same. And they're both going to be, they'll both be the same, and they're going to be that rotation. That's how far we'd have to rotate that to line up that axis with this reference over here. You guys done any geometric dimensioning tolerance, right? A little bit? Talk about a datum. That's your reference line or whatever. Datum, yep. Trying to line that up so that we have that all lined up with our datum. So let's calculate that. How do I find that angle based off the information given here? I could find the length of that line doing that. You're absolutely correct. If I wanted to find the length of this line here in brown, 2.000 squared plus 3.000 squared, square rooted. Inverse tangent, okay. Inverse tangent will find that angle of opposite of 2 over adjacent of 3, right? (33.69 degrees). So that's that rotation. If we rotate that block 33.69 degrees, it'll line up that axis, that diagonal on the bottom of the block with that, we'll call that x-axis datum. So I want you guys to try one. Yes, I realize I'm gonna have to give you some time just to sketch out the picture. So let's say this is 2.850 inches, 1.115 inches, 0.925 inches. And I want to find again across the bottom. If I wanted to line that up with this, how far do I have to rotate it? So it is that angle right here is what we're looking for, right? How do we find R? Perfect. Inverse tangent 1.115 or 2.850. (21.367 degrees). So that's how far we have to rotate it. Now our next step, in a block like this, what if I wanted to find the distance corner to corner like that? So I want to find that red length, we'll call it L for length. Okay, which sides would I use? Okay, so I'm going to label this A, B, and I'm going to call this D for depth. Actually, you know what? Let's be more realistic. Oops. Oh no. I'm going to call them X, Y, and Z. That green line down there, I'll call it G for green line. G, well, I'm just going to do this. G is equal to the square root of X squared plus Y squared, right? L is equal to the square root of G squared plus Z squared. However, G is the square root of x squared plus y squared, right? Okay, I realize I just wrote a lot of nasty symbols up here, but what is the square root of x squared plus y squared squared? Well, what happens to the squared and the square root? They cancel out. That just is x squared plus y squared. L is the square root of x squared plus y squared plus z squared. This is actually called three-dimensional Pythagorean theorem. So a squared plus b squared equals c squared works in one dimension, or in two dimensions, in flat. But if we have three dimensions, we can take all three dimensions and square them. And it gives us that length squared. So let's plug in those numbers here. We've got the square root of 2.85 squared plus 1.115 squared plus 0.925 squared gives us a length of 3.197 inches. Now, could we have just found G across the bottom there and then use that again? Sure, we could have. But what are the disadvantages of that? Yeah, we're going to be taking an answer, rounding it off, and then using it again. So if I just take all three dimensions and combining them at once, I'm avoiding that risk of rounding off the answer and that round-off error becoming significant. One of the biggest obstacles in calculation and machining, mechanical design, and stuff like that is the round-off error. It's called tolerance buildups, round-off error buildups, and stuff like that. Where, yeah, you round it off and you're losing a couple 10,000ths at first. But if you keep reusing that measurement, that round-off error, in the next calculation, it's magnified. Well, let's take a look at it. Let's do G here, where it would have been the square root of 2.85 squared plus 1.115 squared. Let's see how that turns out. Oh, nothing wrong with this. So 3.060. So then we would use that to find L. 3.060 squared plus 0.925 squared. Now I've got to make sure I clear my calculator. I'm not going to reuse that as an answer because that wouldn't be rounded. So here, 3.197, it still comes out to the same, but you'll notice before it was 3.1970, now it's 3.1967. It's going to round up to get there. So it was a few 10,000s difference. Not huge, but it's, if we were to keep reusing that calculation, it could be there. One of my first experiences with actually doing error analysis in I won't say a practical application because it wasn't a practical application. I was working with Professor Albert Irwin, who was actually passed away in 2012, passed just a few years ago. But at the time, in 1995, he was one of the top 5 nuclear research physicists in the world. Had been nominated for the Nobel Prize once at that point. Was nominated once more before he retired. Never won it though, so not that big of a deal. Sorry, but anyway, he did work with semiconductors, trying to create more efficient semiconductors for photocells. And his research team thought they had found, after 8 months worth of work, thought they had found a significant change in the emission spectrum. You guys talk about emission spectroscopy at all in your inspection class? It's like an X-ray, almost like X-ray, but you bombard it with light, and the material absorbs the light, and then when you stop bombarding it with light, it re-emits some of the light, and that tells you what atoms, what elements are actually in that material. It also has a little to do with the structure of the elements within that material, but they thought they had found by doping silicone with germanium, they thought they had found a new emission spectrum. They created a new emission spectrum. Well, I came onto the team as a 21-year-old arrogant kid. My first job was to go through the error analysis, double check the error analysis in their calculations. Well, starting out, a couple of 100,000 was their error in their first measurements. By the time you went through all of their calculations, the propagated error in their calculations was larger than their result. So it did not make for a very happy Professor Irwin, but he did redo the experiment, and in their second run through the experiment, they found that their significant result that they had found was actually not true. It was a result of error in one of their machines. So saved him from writing a paper that would have made him look really, really stupid. But that's how important error analysis is. Dealing with that, using rounded off answers. I don't expect you guys to do the analysis of how big that error is going to get as you reuse it. And here we're only using that calculated answer once more. If you get into a spot where you're going to use it 5, 6, 7, 8 times more, it is a big deal. While we're here, I'm going to look at this angle here. I'm going to call that angle capital A for now, because technically the angle we're going to look for is going to be this angle at some point. We're going to call that angle T, but let's look for angle A right now. How would we find angle A? This is angle A. We know this is 0.925. What else do we know about that triangle? This is that L that we just found, isn't it? 3.9 or 3.197. This down here? Well, yeah, we did find that. The 3.060. We could use that, but if our purpose was to find this length here, we may not have got this amount. Right? We may have skipped over it, did the three-dimensional. So using those two, can we find A? Yeah, this is which side of the triangle over here? Opposite in the 3.197? The hypotenuse. Opposite and hypotenuse make what trig function? Sine. So it is the inverse sine of 0.925, that's the opposite, divided by 3.197, the hypotenuse. (16.82 degrees). What if I did want to know this angle up here? Yeah. What if I wanted to know that one and not this one? Could I have found that one first? Yeah, it would have been, instead of sine, it would have been cosine, because it would have been adjacent. This would have been the adjacent side instead of the opposite side. Adjacent of 0.925 over 3.197. Notice this amount in here is the same. The result I'm going to get here if I punch it in is going to be 83.18, not 83, 73.18 degrees. How do I know that? Yeah. But I also know that the sine of one angle is equal to the cosine of its complement. Remember, this here is the sine of this angle. This is the cosine of that angle. That's why the inverse cosine, inverse sine work on them. The sine of one is equal to the cosine of its complement. So if I have that same number, or in this case, that same ratio, the sine, inverse cosine will give me different angles, but those angles will be complements. They will add up to 90 degrees. What do you think? Better than a stick in the eye? How sharp is the stick? I'm asking that. I'm going to give you 6 problems to do here today. I'll get the packet out to you in just a second. The trickiest parts of this unit is going to be looking at those, boxes and seeing, okay, this triangle lies flat, this triangle stands up. Later, we're going to cut a corner off that box and see this triangle lays on the slope surface on the corner. So it's going to be seeing where those triangles are because they're not all going to be on the same plane. So that really is going to be the tricky part is allowing yourself to visualize those triangles and get them to pop up out of the page at you where you need to.